I'll be doing your lecture today. I hope we have some good chalk, because I plan to write down a lot of stuff. So last time, you found that non-relativistic momentum, which is the sum over m sub I, u sub I, is not conserved when you change reference frame. Is that a fair assessment?
What's that?
Non-relativistic? Can I abbreviate? You may find my sometimes cryptic. I try to sort of write as little as possible. Okay, but physical laws. And you did Einstein's two postulates, right? What are Einstein's two postulates? The speed of light is constant in all frames, and there's one more.
Physical laws apply the same in all frames.
The physical laws are the same in all different reference frames. Otherwise, you could distinguish a special frame if there's some experiment you could do. Okay. So if we're having this, the physical laws are frame independent, then either there's no conservation of momentum, either that law was wrong, which nobody would believe because there's a large amount of experimental evidence in favor of it, or the expression is wrong. And it turns out that the expression is wrong if you write down for a single particle P equals mv, okay? The momentum when you did P1, right? Okay? This is the non-relativistic relationship. The relativistic one is it's equal to gamma m v, okay? And if you write this down in the notation that the book is using to distinguish between v, because this v, if you're doing particle physics, you're just going to write down gamma mv. But the thing is that that's how fast is the frame. Right? You have this picture all over the place that you're kind of used to writing down. V seems to be reserved to show the relationship between these two frames. Okay? So you write this down in the more elaborate notation. And, well, it's like that. It's equal to gamma mu m mu. Now there's something that there's something that you need to be a little bit careful about, and so what I would like to do is look at the components of this. Okay? What's p sub x? This is a vector, right? You love vectors, don't you? Vectors are great, okay? So what's the x component of this vector? Gamma m v sub x. And what's this gamma? Is it the same as this gamma? No. It's the same. Okay? You have to be careful about that. Okay? Gamma u is 1 over, well, let me write it the way I like to write it. I like to write it this way. I might as well write it this way anyway, since you'll get used to seeing how I write it. I write it that way because it fits on one line. So conserve paper. Okay? Which is easier, it's an easier way to do if you're doing mathematical manipulations, I think. It makes everything cleaner for me. And here, this guy, u squared is equal to ux squared plus u sub y squared plus u sub z squared. Okay? So the momentum in a particular direction now depends on its total speed through the gamma and through the particular component and its speed in that particular direction. That's a little bit different. Okay? You have to get used to that and do not write u sub x here. Okay, that's a common stumbling block. Now, one thing that's kind of we started off saying that one of the reasons why we need this guy, and I didn't derive it, it's derivable, and if you take graduate E&M or particle physics, you'll derive it. So. For some of you, we're not leaving anything out. Okay, but we're not going to bother to drive in this class. But I do want to motivate this another way. Did you not derive, or I don't know if Professor Schutt did this in class or not. Did he do, say, u sub y prime is equal to dy prime dt prime? Did he do that in class, or did you just do that from the book? You remember you did the velocity transformation, okay? You did u sub x prime is equal to dx prime dt prime, and then it turned out to be 1 minus ux v over 1 minus, is this right? No. It's ux minus v, was it this? Did I have this right? Ux v over c squared. Do I have the signs right? Okay. So you did this, you started from here and you got to here, right? And the thing is that this dt prime, you do the same thing, right? And you'll get this, and you'll get a relationship like this, except there's a gamma and stuff in there. And why does u sub y prime change, right? It's not because dy prime changes, because there's no length contraction in the direction perpendicular to the motion, right? It's because dt prime changes. Is why your velocity components change from one frame to another, even the ones that are not. Obviously, the parallel one changes. That changes according to Galileo as well. Okay? But the perpendicular ones change too in relativity because time itself is measured differently in the different frames. Okay? And this brings up something that I think is just as bad as this momentum non-conservation problem. Okay? If you have, say U1 and let me do it this way. If you have u sub 1 is let me call it u in the y hat direction. Some number like 10 meters per second in the y hat direction, okay? And you have another one which exactly cancels out the y components. Another vector u sub 2, which is partly in the x direction, partly in the y direction, okay? And I encourage you to do the math if you want. The way I've drawn this, the non-relativistic momentum, P non-relativistic equals 0 in the y direction. Right? You have one particle going up, the other one has the same sort of going down, but it's also going forward a little bit. Okay? So that their non-relativistic momentum mv cancels. Okay? What happens when you transform them into another frame, to those y components? Do they still cancel? is the dt prime different? What was that, what is that relationship? Let's just write one of them down. Let me see if I have it somewhere here. Unless someone knows it. I think I have it written down here somewhere. U sub y prime is equal to u sub y divided by gamma v times 1 minus u sub x v over c squared. Okay? So notice that this depends on u sub y, which is the same in both cases. It depends on gamma sub v, which is the same in both cases. That's just the speed of the frame. It also depends on u sub x, which is different in both cases. For one of these particles, it's equal to 0. For the other one, it's not equal to 0. Okay? So the change in their clocks is different from one frame to another, which means that this is really weird. You have 0 momentum in one frame, and I encourage you to work this out for fun, of course. You know, you should be doing physics for fun. 0 momentum in one frame becomes non-zero momentum in another frame. That's pretty bad, right? I mean, if you think that, because what is a non-zero momentum? What does a non-zero momentum mean?
There's some kinetic energy associated with the particle.
Yeah, there's some kinetic energy associated with the particle. Also, if you have a non-zero momentum, so if I have a system where the momentum of the system is non-zero, that means the center mass of that system is moving, right? Okay? And so if this was your momentum in one frame, if this was true if this non-relativistic result was true, that would mean the center mass is moving in one of these frames in the y direction. How could that be? Right? I have the center of mass not moving at all in the y direction in the one case, and I'm moving in the same direction, right? How could the center mass of that system be moving in a different frame? That doesn't make any sense at all, does it? I mean, I think that even makes less sense than momentum not being conserved, okay? So there's definitely a need to redefine momentum. Okay, let me see, where do I want to go to here? Oh, one thing I want to caution you about, this kind of relates to this, is that the book will sometimes switch to one-dimensional relationships as you're going through it. I noticed this when I was reading it carefully last night. I mean, you know that momentum's a vector. Let me see if I can find this. So, for example, equation 2-23. Equation 2-23, okay, is in 1D. It only considers momentum in the x direction, okay? And how can they get away with that? Well, if you work through the mathematics, you'll see that if you use the relativistic transformations, use the relativistic transformation for gamma, that the x and the y and z components of the momentum don't change in relativity, which is exactly what they do in non-relativistic. Okay? So that's another virtue of this formulation. It's another indication that this is correct. Is that if you have a general three-dimensional, if I have these two frames, S prime with V and S, and I have here some P, which has some y component, and I transform into this frame, it's going to be more tilted this way, to have a p prime, okay? The y component of the momentum is the same. That's what you expect. That works when you have the p is gamma u m sub u, okay? So it means that when you switch frames, only the momentum in the direction of the frame, only the momentum corresponding to the relative motion of the frames is changed. The other two components are not. Now let me see, how much this stuff should I write down? I'm going to write down a little bit of the stuff in the argument surrounding equation 2-23. Let's see. I want to do this part. Okay, you're going to show this. Oh, this chalk is much better. Gamma u prime is 1 minus. Wait. Use my eraser hand. U sub xv over c squared. Gamma u, gamma v. Okay. And you're going to. No, actually, maybe you're not going to drive it. But that's problem 67 if you want to. It's a reasonable thing to do. If you do, I don't think it's assigned, but it might be. I posted the homework today. I didn't really check what all the numbers are. It's useful to, if you work that out, just to get practice with manipulating the gammas. And the thing is to help you make sure that you understand what the different pieces of these equations mean. Okay. So what we want is we're going to just look in the one-dimensional, and what the book shows, using this, what they jump to, using that transformation, is P prime total is gamma V, P total minus V, gamma V, the summation over I, gamma u sub I, m sub I. Okay? Now remember what we want. We want conservation of momentum. And let's go back. Let's look at the non-relativistic case as well. Non-relativistic, P is m sub, we'll call it m sub u, okay? And P prime is m sub u minus v, right? It's something like that, okay, for each particle, right? So you can write this down as, this one I can write down as P minus m sub v, okay? And you can imagine changing this into a general argument over a bunch of particles by putting a summation over I here, and I there, and I there, and make this one now a total, and make this summation over I of m sub I, okay? And then this non-relativistic version, which is kind of useful to look at, to compare with the more complicated looking relativistic version, okay? Now, if you have this non-relativistic version, and you tell that momentum's conserved, and it doesn't matter if I'm on the boat on the quiet sea that Galileo imagined, and if I do conservation of momentum experiments, they should agree with someone sitting at home in Florence when they do conservation of momentum experiments, and it shouldn't matter our relative motion, and if they're looking at the objects I'm smashing together, or I'm looking at the objects, they're smashing together, it should all work out. We should be able to switch between the two reference frames. Everything's non-relativistic, okay? So this is the total momentum maybe on the boat. This is the total momentum maybe in Florence. We're saying both of these are conserved, which is another way of saying if these are both conserved, these things are just numbers. Something I measure before the collision that's the same after the collision. It's just a number, okay? And so what does that mean? If those are both conserved, what's that mean about this thing here? No, but if V were 0, it would be. You're on the right track. If this is a number and this is a number, okay? Let's say this is a number called A, and this is a number B, and I do A minus B, and they're both numbers, what do I get? I get a number, right? Okay? I get a number. So this is a number. So when we transform that into physics language, that means this is conserved. Okay? So if this is conserved and this is conserved, then this must be conserved. Okay? And this is just said, this is non-relativistic conservation of mass. Right? I mean, that's something you learn in chemistry or something. Right? Mass is conserved in chemical reactions or something like that. Okay? And that's something that you use in physics 1. The masses of particles don't change when they're bouncing around. In physics 1, momentum and mass are conserved in collisions. Momentum and mass. Those are the two things. Okay? Well, we have something else over here, and it's not mass. Okay? Now, there's something else that's interesting about this relationship. Let me write it this way. Gamma V, P total, minus gamma, minus V, summation over I, gamma, mu sub I, U sub I, M sub I. Compare this to the following. X is equal to gamma, or x prime is equal to gamma x minus VT. Do those relate, do those equations look very similar at all? Can you see that if I wrote this as gamma P minus V times omega. Now does this look similar to that? Okay? It's like this basically tells you that space and time are getting mixed up in relativity. And this one here is telling you that momentum and something else are getting mixed up in relativity. That they're sort of interdependent. Okay? And that thing that is getting mixed up with momentum is called energy. We write E is equal to gamma m c squared. And if I want to, I can put a little u there. I don't know if I need one. Okay? That's energy. So this thing right here is the summation over I of E sub I divided by c squared. That part in the brackets. That's adding up the energies. I'm adding up the energies of all the little particles. Is what saves this conservation law. Okay? Which we're kind of willing to go along with because we're familiar with energy conservation. Energy conservation was known pre-relativity in certain situations. But the thing is that it's got that mass in there, and so we want to discuss a little bit about how this all plays. I want to discuss a little bit about how all this plays out. So we found this new thing. It's the energy of a particle. Okay. Suppose you're at rest. That means the gamma equals 1. That means that energy is equal to mc squared, which is something that you've heard, like, of Einstein's most famous equation, perhaps, E equals mc squared. And what is this thing? This is something new. This was a big surprise. It's saying that basically that mass is a form of energy. We call this has different kinds of names. We call this sometimes the rest energy. It's sometimes called the internal energy. This thing here, this M, is called rest mass. It's basically the energy that an object has when there is no motion. Okay, let me just continue with this, and we want to kind of connect it to our non-relativistic understanding. Let's see, maybe this piece is good. Suppose that the speed is much less than the speed of light, okay? And let's look at gamma. It's equal to 1 minus v squared over c squared to the minus 1/2, okay? This has the form, this is something that you should remember. It's commonly used. This is a Taylor expansion. It's the first term of a Taylor expansion. You're going to use this again and again. We use it when you're in the quantum part of this too. It's often a way to solve these things when you have these square roots in there. And if you can make an approximation, you can turn an intractable algebraic mess into something you can actually deal with, okay? But in this case, we're going to use it for a physics principle. So if we follow this rule, gamma then is equal to 1. The exponent's minus 1/2. I have a minus times a minus then. So this is plus 1/2 v squared over c squared. So this says that the E, which I multiplied this by mc squared, is equal to mc squared plus 1/2 m v squared, and then there's other terms that we're leaving out. This is our old friend from P1, kinetic energy. Okay? So you can see that in the non-relativistic limit, that this relationship, which is now how you should think of energy, is, that should be your energy equation. 1/2 mv squared, until you get to quantum, that's out the window. Okay? You'll want to use it, but don't let yourself use it. It doesn't work anymore. Okay, it's now gamma mc squared. And you say that we're going to define the energy equal to the mass energy plus the kinetic energy. Okay? This one down here is the non-relativistic kinetic energy. Okay? This one here, this is the relativistic kinetic energy, which you can say then is that the relativistic kinetic energy is equal to E minus mc squared, or is gamma minus 1 times mc squared. I just put a gamma mc squared in here, right? So that's our new that's our new kinetic energy. This is my, I think this relationship encapsulates things. I think it's more useful than this one. Okay? So these are the basic the two energies. The energy is gamma mc squared, which is okay as long as the thing that you're talking about has mass. If it doesn't have mass, that doesn't work. But there's a relationship that does work, even if that doesn't have mass. And then I remember this one because I can always easily get to here from here. And then if you just remember that mass is energy, and if I want the total energy of something, I add its mass energy and its kinetic energy. That's how I remember this, okay? It's simple. Energy is just the sum of the mass energy and the kinetic energy. Now, if you have the situation where V is much less than C, then if you look at the mass energy divided by the kinetic energy, this is equal to, let's see, mc squared over gamma times 1 minus mc. Do I have this all right? I want the mass energy divided by the kinetic energy. I think I have that right. No. You guys have to stop people when they write dumb things on the board. Okay? You have to stop us. That's gamma minus 1 mc squared, right? Okay? These guys cancel. Okay. So if the speed is much less than c, then the ratio of the mass energy to the kinetic energy does what? Goes to 1. What is gamma for V much less than C? It's pretty darn close to 1, right? So what do I get here? I get a 0, which means this goes to infinity, right? Okay? So if you have something, I mean, it's just, it's basically saying that if it's not moving, okay, it has no kinetic energy. So basically all of its energy is pretty much in the form of mass. Let me see. I wanted to show you. I want to show you maybe another way to look at that. Let me tell you something. Let me first tell you something else about what this E equals mc squared means. Trying to find the softer chalks which are easier to write with, and it's not so easy. Let's consider a box of ice and a box of water. And the big picture, the energy in the ice is equal to the mass of the ice times c squared. The energy in the water is equal to the mass of the water times c squared. Let's suppose further that you have the same number of molecules. Same number of molecules in the ice, same number of molecules in the water. Which one weighs more? The water does. The water weighs more, okay? if you have the same number of molecules, okay, then you have summation over I, gamma I, m sub I, v sub I. Or wait, what's the v in there? M sub I, c squared, right? The molecular, if I wanted to figure out the mass of the ice, it would be fair to just add up the mass of, if I wanted to figure out the total energy of the ice, it would be fair to add up the total energy of every little particle, right? That would be a reasonable way to do it. And you also have, of course, binding energy and stuff like that.
Could you explain one more time why water weighs more than ice?
That's what I'm trying to do. Okay? Trying to do that. So you have the ice, you have the water, they have the same number of molecules, right? So to get the total energy of the water or the ice, I want to just add up. E is the summation over E sub I. I'm going to add up all the little bits of energy in the water or in the ice, okay? Now, what do you know about the I'm going to write this thing here. We haven't seen this yet. You'll see this in quantum a lot. This means an expectation value, the same as a mean, an average. What do you know about the expectation value of gamma in each of these cases? Yeah, it's going to be near 1 in each case, but how about if you compare the water to the ice? Is there going to be a difference between them? What's the difference between water and ice, right? In water, if you like to, I can say ice and superheated steam. Okay? Okay? So the difference is that there's more rattling around. So that in water, basically, the things have become unbound. Each individual molecule has a lot more motion. It's moving all over the place. In ice, it's basically staying there. So in water, the gammas are higher. Okay? So if I add it all up, I get a higher total energy. Okay? But if you're looking at the big picture, you're looking at this from outside, I'm just putting this thing down on a scale and weighing it. That's all I'm doing. Okay? And that's what we're calling the mass. Right? You take your sample, you stick it on a scale, you weigh it, that's what we call the mass. Okay? The relativity says that that's the total internal energy. That we're measuring the rest energy. Okay? So the point is that mass is energy means that everything else being equal, hot things are heavier than colder things. So if you're looking from the outside of the big picture, then the mass represents all the forms of internal energy. Okay? So the mass is the internal energy. Okay? You have the constituents. You know what all the little particles are made of. You have the kinetic energy of the constituents. And you have the inter-particle interactions. These can be negative. This can be negative energy. If it's negative energy, an example of this is, and you'll run into this a lot when you do the quantum, is binding energy. So if you take, when you take, two particles like a proton and a neutron, and you fuse them together to give you a deuteron, which is one of the things that has to happen in the sun for it to shine, it gives off energy. In the case of the sun, that energy ends up being converted, some part of it, into light. Okay? That's a binding energy, okay, is negative. It sort of makes things stick together. We're bound to the earth. We're stuck to the earth. That's why it's called a binding energy. And binding energies are always negative. Okay. One of the take-home messages from this stuff, and you have to get used to it. Mass is not conserved in relativity. Okay? I mean, we've learned already we can change the mass of something just by heating it up. Of course, you may say that's cheating, that's doing work on it. You also have the case where you can have a particle, say a neutron, decay into a bunch of stuff, a proton, an electron, and a neutrino, for example. Neutron decay. And if you take the masses of these three particles and add them up, you will not get the neutron mass. Mass is not conserved in relativity. What's conserved? Energy and, not mass, momentum. Energy and momentum. And when you did P1, you had mass and momentum conserved. Now you have, now mass is no longer conserved, and the thing that's conserved we call energy. People used to call that, but we don't do it anymore. I mean, it's sort of semantics. Instead, you could say, and you'll see this in some older physics books, okay? But don't write this down, okay? You promise me? Promise? Don't write it down, okay? Don't write this down. You'll see this in a lot of older physics books. So they used to say that the mass depends on the state of the motion, okay? And we don't, wait, there's no c squared there, sorry. We don't use that terminology anymore. But you could basically talk about things in the same way and use different words and call things different. It's better to just keep m to refer to the rest mass and call this energy. At least that's the convention. That's the convention of the way, of the day. And a lot of what you do in physics is conventional. And that's all right as long as you can predict your experiments. Now let me see. I wonder if I don't know if I can do this. I want to do this example of this to get you used to this. I want to do this in I want to just, maybe I think I might have enough time to do this if I do it fast. To just get you to used to doing energy momentum conservation in relativity like you did before in P1. Okay? If we want this collision, we're going to take the energy of the neutrino equal to 0. So it's an infrared neutrino. It's a neutrino we don't care about. To make this easier, we're just going to do a two-particle right-hand state, which would sometimes, very rarely, actually happen in this decay. It's basically equivalent to having a very low energy neutrino. We're going to neglect it, is what I'm saying. Okay? So this is a decay process. Before, we have a neutron sitting here. After, we have a proton. We call that V1. And an electron. We call that V2. Okay? That's our process. So you want to write down conservation of momentum. I write 0 is equal to minus gamma 1 V1 m sub p plus gamma 2 m2, no, V2 m sub e. Right? The momentum 0 on the left hand, it stays 0, but it's the 0 momentum is shared among these two particles. I think I wanted to write m sub e there. Okay? Proton, electron. Do you know, how much do you know about a proton and electron? How do they compare? Yeah, proton's big. A proton's big. A proton and a neutron are about the same size, about the same rest mass, and they're very big compared to an electron. Okay? That'll be useful later. We want to write energy conservation. How much energy do I have on the left-hand side? I have the mass energy, right? Okay? You have to get used to including that. M sub n c squared is gamma. Gamma 1, m sub p c squared. Don't forget to put in the gammas. That's a common error made when trying to work these problems out on exams and so forth. Especially on exams. On homework, you have time to make sure you get that right. Okay? Don't leave out the gammas. Oh yeah, yeah. Thank you. That's exactly what you should do. When we write dumb things on the board, you gotta let us know. Because really, I'm a single tasker, but when I'm lecturing, I'm multitasking. So it's a problem for me. Right? Okay? Now the thing about this is, you kind of need to practice solving these things to kind of know what you're doing, okay? Whenever you get one of these and you're trying to solve this, I'll tell you this, you're going to square these equations. You're going to have to shuffle them, and then you're going to square it. And then you're going to add it, okay? And you just have to kind of guess what's going to work until you sort of get good at it, okay? So what I'm going to do is I'm going to write this one this way. I'm going to write gamma 1, m sub p, I'm dropping the c squared, is equal to gamma 2, m sub e, minus m sub n, right? That's just this equation rearranged without the c squares. Then I'm going to square. Gamma 1 squared, mp squared, is equal to gamma 2 squared, m sub e squared, minus plus m sub n squared, minus 2 gamma 2 m sub e m sub n. Then what you want to do is you want to take this other one, take this one and make it look something like this. So since I took the m sub p over here, I'm going to take this over here and I'm going to square it. So we're going to rewrite this one this way. Gamma 1 squared, that should be squared, m sub p squared, v squared over c squared, also divided by c squared for convenience, is equal to, on the right-hand side, this is going to be gamma 2 squared, v2 squared over c squared, m sub e. Okay? Squared, thank you. Then what you do is, now I just add these guys. And let me just point out what's going to happen. I'm going to get a gamma squared times 1 plus v squared over c squared. Okay? What's that? When I add this equation to this equation, okay, I have gamma squared here. I have gamma squared v squared over c squared here. I pull out the gamma squared, so I'm going to have a 1 plus v squared over c squared times gamma squared. What's that equal to? 1. Yeah. This is equal to 1. So you're going to get m sub p squared is equal to m sub e squared plus m sub n squared minus 2 gamma 2 m sub e m sub n is the result of doing this, okay? So note that all that's left is gamma 2. And one of the other things you should remember is you have gamma, that means you have the kinetic energy, that means you have the speed, that means you have the energy if you know the mass, okay? Once you have gamma, you can get everything else, okay? And since I have one of the gammas, I have gamma 2 here, I can go back to, this will be the easiest place to get it. I can go back and get gamma 1 if I wanted that. Okay, so you have gamma 2, gamma 1, the whole thing's solved. Wrap the boil around it, turn it in. Okay? That's all for today.